The Laplace transform of the function f of t is defined to be the integral of 0 to infinity of e to the power of minus s times t times f of t dt. Now, since we're integrating with respect to time, we are going to get a function of s. Now, s is assumed to be some positive number here. Now we can write the Laplace transform of a function like this: L of f of t. Again, s is assumed to be a positive number. Let's take this example. Let's suppose that f of t is e to the power of minus 2t. So we plug that in here for f of t, and we have to multiply it by e to the minus st. The bases are the same, so we can add the powers, and we can factorize t out of the power. Now we're integrating this function with respect to time, so we can treat the coefficient of t minus s plus 2 as just a constant. When we integrate e to the power of a constant times t, we get 1 over the constant times e to the power of the constant times t. So in general, we have a function of the form e to the power of at, and here is its integral, so a is some constant. So that's the situation in this example. The constant is actually minus bracket s plus 2. So we divide by minus bracket s plus 2, and our limits are from 0 to plus infinity. So for the upper limit, we have to take the limit of this quantity inside the square brackets as t tends towards infinity. Now, since we're assuming that s is a positive number, it means that we have a negative power here as t tends towards plus infinity. So we can write what's on top here as 1 over e to the power of s plus 2 times t. And we know that as t goes to infinity, well, the denominator will go to infinity, so this will go to 0 as t tends towards plus infinity. So that's why we have a 0 here. And as for the lower limit, we have a minus sign, then the expression in the brackets evaluated at t equals 0. So on top we're going to get e to the power of 0, which is 1. And the two minuses give a plus here. In the next example, we're going to look at the function f of t equals t. So to get the Laplace transform of it, we integrate from 0 to infinity e to the minus st by the function, which is t in this case. Now we have a product of functions here. We can use integration by parts. So here is the integration by parts formula. So we have to decide which of these two functions is u. Well, this is where we can use the rule LIATE. A stands for an algebraic term, so the algebraic term here is t. E stands for the exponential term. The exponential term is e to the minus st. Since a comes before e in this word, or rule if you like, we let u equal t. So if u is equal to t, then dv, the differential, must be the rest of what's here, e to the minus st times dt. So now the left hand side looks like the integral of u dv, where u is t and dv is e to the minus st times dt. If we multiply t by this, we get this here. So by integration by parts, we have to get v and we have to get du. To get du, we need to differentiate this, so we differentiate this function. Well, du dt is just 1, so we see that du is just equal to dt. To go from dv to v, we integrate. So we differentiate here and integrate here. And as we've seen already, e to the power of a constant times t integrates to give 1 over the constant times e to the power of the constant times t. So now we plug everything in here. For u we plug in t, for v we plug in minus 1 over s e to the minus st. And we have to integrate v du. So here's v, and du is just dt. Now let's look at this expression evaluated as t tends towards plus infinity. Well, obviously, as t tends towards infinity, you know, this part of the product is going to go to infinity. But what about e to the minus st? Well, because s is positive, e to the minus st will tend towards 0 as t tends towards plus infinity. So one part of this product goes to infinity, and actually minus infinity. The other part goes to 0. But this part goes to 0 much more quickly. So the entire product actually goes to 0. So this term dominates while taking this limit. So for the upper limit then we get 0. Then we have to look at the lower limit. We put down a minus sign and we evaluate this expression at t equals 0. Well, if we plug 0 in for t here, we get 0 in this product, 0 times this thing, so we get 0. So we get 0 minus 0, which is 0. Now we can take the minus 1 over s out. It's just a constant because we're integrating with respect to time. So we get plus 1 over s. Now we integrate e to the minus st. We've seen that already. We saw it up here actually. So we just have this here evaluated from t equals 0 to t equals plus infinity. So we get 1 over s, and we have to take the limit of this as t tends towards plus infinity. Well, we have e to the minus st, that's going to go to 0 as we've seen already. Minus 1 over s times 0. Then we have a minus sign, and then we have to evaluate this at 0. Plugging 0 in for t, we get minus 1 over s times e to the 0. That's minus 1 over s times 1. So we get 1 over s squared. Now let's get back to the unit step function. We've seen this already. And let's consider another unit step function. It's called u of t minus 3. So I will compare this new function to u of t. We saw that u of t is equal to 1 if t is greater than or equal to 0. So I'll show that sketch again here. So here's the graph of u of t. Now to get u of t minus 3, we replace t with t minus 3. So we have the same statement here, we just make that replacement. So u of t minus 3 is 1 if t minus 3 is greater than or equal to 0. But if t minus 3 is greater than or equal to 0, it means that t is greater than or equal to 3. Just bring the minus 3 over. So the function is equal to 1 when t is greater than or equal to 3. Now u of t minus 3 equals 0 if t minus 3 is less than 0. So again, our first unit step function said that u of t equals 0 if t is less than 0, so we just replace t with t minus 3. So if t minus 3 is less than 0, it means that t is less than 3. So for t less than 3, this new function, u of t minus 3, is 0. So our new function looks like our original step function. But the step occurs not at 0, as it does here, but at 3. The step occurs at 3. You know, you can think of u of t as just being u of t minus 0. So the step occurs at this value. So here's the general situation. U of t minus a is a step function which is 0 for values of t less than a, but 1 for values of t greater than a. Now in this example we are going to consider the product of some function with the unit step function u of t. So the function we are taking is sine of t, and we're multiplying it by u of t. So since u of t is 0 for values of t less than 0, we will be multiplying 0 by this part of the function. So it'll just kill it off. So we just get 0 here. We just get a horizontal line passing through 0. But for the part of the function over here for t greater than 0, we are multiplying it by 1 because u of t is 1 for this region. And if we multiply a function by 1, we don't change it. So this part of the function is unchanged. So now we have a causal function. It's 0 for negative t. Here's another example. We're taking the same function as before, sine of t, but this time multiplying it by u of t minus 1. U of t minus 1 is a unit step function with the step at t equals 1. So it's 1 for t greater than 1. and it's 0 for values of t less than 1. So when we multiply 0 by sine of t, we get, of course, 0. And if we multiply 1 by sine of t, well, we just get the function. So we could say that we switch on the function sine of t at t equals 1 by multiplying sine of t by u of t minus 1. Now we can also imagine switching on and switching off signals. Let's take this example here. Let's first of all consider the function u of t minus 1 minus u of t minus 3. Let's take the graph of u of t minus 1 first. Well, the step occurs at 1. So I'll do that in black. So in black we have the graph of u of t minus 1. Now in red I will show the graph of u of t minus 3. So the step occurs at 3. And for t greater than 3 the function is equal to 1. Now in blue I will get the difference of these functions. That is u of t minus 1 minus u of t minus 3. So let's look at values of t up to t equals 1. Well, both functions are 0 there. So we will have 0 minus 0, which is 0. So we're going to get 0 for values of t less than 1. Now what about values of t between 1 and 3? Well, u of t minus 1 is equal to 1, but u of t minus 3 is equal to 0 for all values of t between 1 and 3. So we get 1 minus 0, which is 1. So we get this piece here. We get 1. That's for all values of t in here. What about values of t greater than 3? Well, both functions are equal to 1 for values of t greater than 3. So we get 1 minus 1, which is 0. So we get 0 for values of t greater than 3. So our function is just a horizontal line of height 1 for values of t between 1 and 3. It's 0 elsewhere. So now suppose we multiply this function by some general function f of t. What will the effect be? Well, because it's 0 for values of t less than 1, we will be multiplying 0 by our function. So f of t here is the function shown with the dotted line. So we're multiplying 0 by this bit, and we're just going to get 0. So we're just going to kill off the function for values of t less than 1. Similarly, for values of t greater than 3, u of t minus 1, u of t minus 3 is 0, so we're multiplying 0 by f of t. So we're just going to get 0. However, for values of t between 1 and 3, this function is equal to 1. So for values of t between 1 and 3, we're multiplying 1. This becomes 1 inside the brackets times f of t. And 1 times f of t is just f of t. So we've just picked out this part of the signal, or the function. So this line here is really part of the function. It's just f of t times 0, which is 0. And similarly, this line here is really part of the function, but of course we're really just interested in the part of the function for values of t between 1 and 3.